This study tackles an important challenge as LLMs become more widely deployed: how to make reasoning more efficient without sacrificing performance. The authors systematically evaluated 31 different prompts across multiple models and benchmarks. They discovered that no matter how you compress the reasoning, what matters most is simply the length of the reasoning. This insight has significant implications for making LLM inference more cost-effective. Section 3 explains the methodology behind token complexity. The researchers generated responses using 31 different prompts for each question and observed whether performance exhibited a threshold behavior. They developed a threshold classifier that predicts whether a model will solve a problem based solely on response length. Remarkably, this simple classifier achieves over 90% accuracy across models and benchmarks. This suggests token complexity is a robust measure of task difficulty that works independently of specific prompting strategies and provides a foundation for theoretical analysis. Table 3 reveals the efficiency gap between current practices and theoretical limits. While Be-Concise prompting reduces token usage by 20 to 40% compared to standard chain of thought, theoretical calculations suggest we could achieve 311x compression without sacrificing accuracy. This gap is especially pronounced for simpler problems in datasets like GSM-8K, where up to 11x compression might be possible. The table provides concrete evidence that current prompting strategies are operating far from optimal efficiency, suggesting significant room for improvement in LLM reasoning efficiency. Section 4 applies information theory concepts to derive theoretical limits for the accuracy compression trade-off. The authors modeled this as a knapsack problem. Given a token budget, which problems should we solve? The optimal strategy prioritizes problems with the lowest token complexity. This approach yields a mathematical upper bound on achievable accuracy for any token budget. Importantly, the gap between current methods and these bounds is substantial, especially for challenging datasets. This suggests that significant advances are possible in reasoning efficiency beyond current prompting strategies. Sections 5 and 6 explore whether LLMs adapt their reasoning length to problem difficulty. The good news is that models do exhibit some adaptive behavior, using shorter chains for easier problems. However, this adaptation is relatively weak, correlation coefficients of 0.2, 0.5. The authors propose prompt routing to improve adaptivity, using different prompt strategies based on estimated problem difficulty. While uncertainty-based routing, using token probabilities, shows modest improvements, verifier-based routing, using knowledge of which problems are solvable without reasoning, performs much better, approaching theoretical limits. Figure 4 visualizes the performance of different routing strategies. The red curve shows all standard prompting strategies follow the same Pareto frontier. There's no magic prompt that breaks this trade-off. Uncertainty-based routing, purple dots, offers modest gains by using model confidence to selectively apply different prompts. Verifier-based routing, blue dots, which knows when problems can be solved without reasoning, achieves dramatically better performance, approaching theoretical limits. While perfect verification isn't practical, this result demonstrates significant potential gains from better problem difficulty assessment. The key takeaway is that there exists a universal trade-off between reasoning length and accuracy that holds across diverse prompting strategies. The paper introduced token complexity as a fundamental measure of problem difficulty, showing that each question has a minimum token threshold required for successful solving. Current compression strategies are far from theoretical limits, suggesting substantial room for improvement. The most promising direction is adaptive compression, using shorter reasoning for easier problems. This work provides valuable benchmarks and theoretical foundations for future research on efficient LLM reasoning.